I don't know.
So let's chit chat about the lab.
The lab is going great.
Well, good.
It's so.
So you had this action going, right?
Yeah.
And the idea being, on the initial assumption that you're making, is that when this thing is going around like this, here's your rubber stopper, it's being swung around, here's your glass tube, there's your weight on the end of it. So the first assumption that we're going to make is that whatever the weight is on the end of the string is what's creating the centripetal force to keep the rubber stopper moving around. Okay, so that's the first assumption that we're going to make. So on that data table, where that column where it says centripetal force, that's just going to be the weight of whatever's hanging down. So initially, we're going to change the weight. Louis, where's Pop?
I have no idea.
Okay. So initially, you're changing the weight. No, it's gone. So centripetal force equals mv squared over r. So in all of these trials, you're going to have four variables: centripetal force, mass of the stopper, velocity, and radius. The one variable that is going to be like the equalizer is velocity. Okay, so where you're never going to hold velocity constant. That's going to be the one that's always going to change to balance things out, because that's what we can control, is how fast this thing is spinning. So here's the main idea. On trials 1 through 4, you made the centripetal force get bigger. Okay? Mathematically, the mass of that stopper and the radius are fixed values. Those are constants. Okay? So mathematically, you could take the mass of your radius, or mass of your stopper, divide that by 0.8, and get a value that has some weird units of kilograms per meter. Okay? This would be a number. Okay? You can get that number. And then times v squared equals centripetal force. So if you're in a math class, this is basically y equals kv squared. Okay? That's it. It's a quadratic equation. Okay? So what this means is that your centripetal force changes as a function of velocity squared. Cool with that? We're good. Okay. Now, when you get to answer these questions on the back side, so let's talk about that. So the first thing you're going to do, you're going to draw 3 different graphs. And if you just want to put them all on one sheet of graph paper, you can. Okay? So the first one, you're going to plot velocity on the y-axis and centripetal force on, velocity on the x-axis and centripetal force on the y-axis. And some of these, I'm going to tell you, 2 of these are specifically going to start at 0, 0. So what should happen is that this gets like a nice quadratic function. Okay? Something like that. So what you want to do when you get to question number 2 on that back side, I said, which of these 4 variables are changed and which 2 are being held constant? So on this one, you're going to say, oh, we're keeping the mass of the stopper and the radius as our constants. Those are the numbers that aren't changing. What we are changing is centripetal force and velocity. So that's all you have to say. Then on number 3, it says, based on the graph, what's the relationship? You can say, you could just simply say it's a direct relationship. If you want to know, we get fancy, you would say, oh, it's directly proportional to v squared. Now, you want the simplified equation, and I tell you, basically, you want to simplify this equation into the terms of what you're going to graph. Okay? The first one's pretty simple. You really don't have to do much to it. But then I'm going to say, explain the results of your graph, simplifying the equation. Keep in mind which variables are held constant, which are changed. So down there on question number 4, you want to give your answer, and you want to mention all 4 variables. Okay? You want to mention all 4: centripetal force, mass of the stopper, radius, and velocity. So here's how you could say this. Okay? Just giving this as an example. you could say, okay, centripetal force and mass mass and radius are constant. So as centripetal force increases, velocity has to increase. Okay, that's all you have to say. Okay, you don't have to get wordy. You don't have to write out your doctoral thesis. Okay, or you could say, as centripetal force increases, velocity has to increase because mass and radius are constant. Just make sure that you mention all four of these on questions 4, 8, and 12. So when you write out those explanations, when you write them out, you make sure that you have mentioned all four: centripetal force, mass, radius, velocity. Okay? If you're not sure, give it to your partner and go, hey, does my answer make sense? Okay, do I have all four variables mentioned? Okay? So when you simplify those, the next two become a little bit more complicated in terms of how you simplify them. But again, if you just keep in mind that you want to simplify that equation in terms of what you're going to graph. So like on that next one, you're going to put radius on the x-axis and velocity on the y-axis. Okay? So you're going to manipulate that. Force centripetal equals mv squared over r. You're going to manipulate those variables so that you can look at that in terms of, oh, this is what I'm going to graph. How can I manipulate that equation so that I have what I'm graphing on the y-axis by itself, a constant, and then what I'm graphing on the x-axis. Okay? That's all you have to do. When you get to question number 13, now we're going to see how good your data actually is. Okay?
What?
So what you're going to do is you're going to go to trial 4, 8, and 12. So what you're going to do, you're going to only do this on these 3 trials, not all 12, just on these 3. So you're going to go to trial number 4, and you're going to calculate centripetal force causing, by this equation, mv squared over r. You're going to know the mass of the stopper. You're going to know your velocity, because you knew the circumference, you know the period. So you're going to know this number, you're going to know the radius. So you are going to calculate centripetal force actually using your data. Mass of the stopper, velocity, radius. Okay? That's going to be like our experimental value. So that's why I tell you, calculate experimental error using the centripetal force calculating the weight as the theoretical value and centripetal force as the experimental value. So you're going to do this, you're going to get a number. So this is my experimental value. So what you're going to do is that you're going to take your theoretical minus your experimental divided by your theoretical times 100. So this theoretical is going to be the mg of whatever is hanging down. Okay? So on trial number 4, you had a 0.4 kilogram mass. So what did you get when you took 0.4 kilograms times 9.8 meters per second squared? Y'all should have that somewhere. 3.92. So what you should get, and this is going to be the same for everybody, you should get 3.92 newtons. You're going to subtract what you get out of that using mv squared over r. Okay? Because that's your experimental value. Then you're going to divide that by 3.92 times 100. Okay? So it's going to be 3.92 minus mv squared over r divided by 3.92 times 100. And you're going to do that again for trial 8, and you're going to do that again for trial 12. Okay? I do not want you to do all 12 of the trials, just those 3. Okay? Now, when you get to number 14, you're going to calculate the centripetal acceleration on trials 4, 8, and 12. And you could use 4 pi squared r over t squared. You could use v squared over r. I don't care. You get the same answer as personal preference. Personally, I'd use v squared over r, but that's just me. So let's say on number 4, let's just make this easy. Let's say that you calculate that centripetal acceleration and you get 19.6 meters per second squared. Okay, you're gonna take your velocity squared divided by your radius. Let's say you get 19.6. So your g's are gonna be that number divided by 9.8 meters per second squared, because it's a ratio. So in this case, you would get 2 g's. So what that means, if that was your number, if you're the rubber stopper, what that means is that your arm, if you go to lift your arms, they would feel twice as heavy. Okay, if you go to lift your head off of your pillow, it would be like, oh, okay, it would feel twice as heavy. So keep in mind, humans suffer discomfort at about 3 to 4 G's, okay? Some will pass out starting around 4 or 5. You get up to 20 G's, that's when you begin to break bones, okay? So just kind of keep that in mind. So all I want you to do is get an idea of what that centripetal acceleration is going to be. When you get to question number 15, you're going to calculate the centripetal force needed to keep the Earth in orbit around the sun. Okay? So on 15 and 16, I would recommend that you use centripetal force equals mass 4 pi squared r over t squared. Don't forget to square the pi. Now, what units does that radius have to be in?
Meters.
Meters. What did I give you the radius in?
Feet, probably? Inches.
Kilometers.
Kilometers. Okay.
Okay?
Plus, yes, inch.
Yep. Now, here's the other thing. What units does t have to be in?
Seconds.
Well, seconds per revolution, but just seconds. Let's just make it simple. It has to be in seconds, right? So how long does it take for our rock to go once around our star? 365 days. What are you going to have to do with those 365 days? Convert them into seconds. Okay? And don't round them. When you convert them into seconds, keep all of those. Now, it's going to be a pretty big number, by the way, because you're keeping the Earth in orbit around the sun. When you get to question number 16, here's the visual that I want. Imagine that Al is standing here. Let's put right the world, okay? And Al is standing here in Kenya, right on the equator. And Al is going around like this. So are all of us right now undergoing centripetal acceleration?
Yes.
Yes, that's a good thing, okay? We're on a spinning rock. If we're not, we're going to go flying off in a straight line tangent. That's bad, okay? So right now, we're all undergoing centripetal acceleration. So what you're going to calculate on number 16 is how much centripetal force is needed to keep that 70 kilogram person on the Earth. Okay? That's what you're going to do. And again, you want to use that mass 4 pi squared r over t squared. I've given you the radius of the Earth. Oddly enough, I gave that to you in kilometers because I'm a jerk. You have the mass. Now, the Earth is spinning on its axis. How long is that going to take? How long is it going to take for Al to go once around the surface? 24 hours, and we change that into seconds. Okay. When you get to number 17, visualize this. Here's this rubber stopper going around like this. Okay. You're going to draw all the forces acting on that rubber stopper as it's being swung around over your head. Okay. Now you're going to have to go to data from number 1. Okay, so you're going to, everybody's numbers are going to be different. So, and I tell you, draw the vectors to scale with a ruler and indicate the scale that was used. These are going to be pretty small numbers because you have a pretty small mass of the stopper. So I'd at least let maybe 2 centimeters equal a Newton, something like that. Okay.
Can we do it on this paper right here?
Yeah, you do it right there. Do it right there. Okay. All right, I'm done. It's a Wednesday. You all have about 55 minutes. Here's what I would recommend. What I would recommend, you by the way, your groups are going to have to join forces.
That's fine.
Okay. Here's what I would recommend. I'd focus on getting your data. Then I draw the graphs to see if you have any outlying data points. If you have any outlying data points, redo those trials, okay? So that way, because if your data looks something like this, okay? Oh, we got a data point here, data point, whoa, and a data point there, something went horribly wrong, okay? So these are, none of these are gonna be linear, but they should, if this makes sense, they should make a straight curved line, which is an oxymoron, I know, but you get the idea, okay? All right, I am done. You're on your own. If you have not handed in that assignment from